Right, good morning everybody. Hope you all slept well. Today I'm going to talk about the machine learning that we implicitly saw yesterday and which left a lot of questions. So hopefully today we will answer those questions, such as how do we identify loops, which is in fact the main thing going on here. I would say loop identification. So I'm going to just backpedal a little bit and remind you where we're coming from. We're trying to use machine learning to reverse engineer models of computation that we can afterwards analyze for problems. And the problems might be problems of timing, they might be problems of logical behavior, they might be some combination of the two, which is very typical in real-time systems analysis, for which you would naturally use a temporal logic where behavior and time are interwoven. That's indeed what we do. We were using model checkers yesterday. So I'll just remind you where this is coming from, and then we're going to spend most of the time looking at a classical algorithm in the field from Dana algorithm, I believe at Yale, even still. And lastly, I'll make some remarks about the complexity, both in theoretical and empirical terms. There are two references here which I think are quite useful to know about. One is the original paper, which is perfectly readable today, very good systematic study that actually goes into a lot of fine technical details that I'm not sure people even understood immediately, but still they're applicable today, such as the stochastic aspect of learning. And recently a colleague of mine, Amel Benasser at the Open University, and we wrote quite a long introduction to machine learning, specifically oriented towards machine learning of models of computation. By a model of computation, what we meant in the paper is some sort of, in some way, extended automata model, okay, which perhaps could go all the way up to a Turing machine. And that's a bit this is not entirely mainstream, I would say, in machine learning. So we are not deep learners, we're not SVM learners. Those techniques are useful in other areas of software engineering, but that's not what's going on here. This is quite a long introductory paper. It has a lot more detail than I'm able to go in today, particularly the mathematical aspects, the congruence concept that's really, in my opinion, essential to understanding what's going on here. And in fact, that's part of a larger book. We held a Dagstuhl meeting on, as you can see, machine learning for software analysis. We held that in 2016. And there's a book which hopefully will come out this summer. It's actually at Springer right now. Hopefully there's somebody there working on it. So it's this volume 11026. You can keep an eye out for that. It'll be out quite soon. And that's a collection of papers in this area. So if you're curious about more machine learning, which is a vast subject, okay, enormous, more than I think any one person is able to track nowadays. So there are those resources. Right, so we went into this architecture yesterday. This is the architecture of a tool, and I break it down into the three main components. A black box system under test, okay, you can't see what's in there, but you can fire in queries, so you can at least, talk to it. You can understand how it talks back. This is normally called the API of a system. Everybody publishes their APIs, otherwise no one could ever talk to anyone. So you can observe its behavior, so you project out certain variables. You typically do not look at all possible variables, and indeed there may be hidden variables in the system, okay? So there are typically hidden and public variables, and you can observe the public variables. So you can watch them, and the point is that in embedded and reactive system, these observations take place over time, okay? So there's a first input, a second input, a third input. Obviously stop after some finite time, which is not necessarily bounded by any number. And you'll typically get a corresponding number of outputs, the first output, the second output, and so on, okay? So this is the paradigm in embedded systems. There are other paradigms because, of course, you can change the computational model in here, okay? You can work with just a procedural program that like a C routine that takes an initial input and it does nothing until it terminates, okay? And spits out an output. That's a different paradigm. That's more closely related to, say, what you would model in Hoare logic with a precondition and a postcondition. So temporal logic is a little bit different. It looks at the stages in between, okay? So obviously there are different models of computation here, and in general they're going to have to be monitored and observed by different kinds of learning algorithms. That's why I tried to point out yesterday that this is a kind of a generic approach to testing, okay? You can change many parameters. Anyway, our focus, as I said yesterday, we didn't really get much attention until we started looking at embedded systems. And I guess it was because this time dimension causes a lot of difficulties for testers in practice, okay? Scheduling things, working out what sequences imply what other sequences. This is an extra difficulty on top of the basic problem of writing a test case, okay? So it's intellectually rather demanding. So we try to automate this. So then there's the learning algorithm. That's what we're going to look at today. I use the word adaptive here. I could just as well have said iterative or incremental. These words are somewhat similar here. They mean that you start off knowing nothing, in fact, but you build up a model in a sequence of steps, okay? So there's a first model, a second model, a third model. Now, naturally, any mathematician would ask the question, do these things converge? I'll talk about convergence as time allows. I can say that in language theoretic terms, so, you know, this thing could be a DFA learner. In language theoretic terms, it's a little bit messy. Nevertheless, for L star and for very many algorithms like L star, you can prove termination and you can prove that the final output is behaviorally isomorphic with the system under test. Okay, that will be an important result we'll see today. So because this is incremental, you spit out a sequence of, let's call them estimates of the final model. Okay, they are incomplete until termination of this procedure. But nevertheless, even early models can be quite useful to model check. Indeed, on the types of systems that we're going to look at tomorrow, which are systems of systems, there's really no chance to get a complete model. They are way too complex, okay? But this does not mean that approximate models are useless or that they have no value. Because as testers, we're looking for errors. And an error you can already find in a model with one state, okay? It's technically possible. So the whole procedure has meaning even if you don't run to completion. So there's the requirement. So you get your model estimate, you get your requirement, you get a counterexample, an LTL, you can strip it off and make a new test case. So there are actually two loops going on here. There's an inner loop where we're building the next model estimate, and then there's an outer loop where we're analyzing that model estimate. And if we find a counterexample, we run it back through, and then look what happens. If it's a true negative, great. There's something that's wrong both in the model and in the system under test. So we'll save that and hand it back to the developers. But if this is a false negative, it means that the model is wrong, and of course the system is by definition the system, so that the observation we get, which is not the predicted observation, that allows us to refine the model. So it's a naturally optimizing process, what is going on here. There's a third source of queries that we'll also see with L star, which is equivalence checking. I factored that out here. Yesterday there was a box over here generating equivalence checking queries. Right, let us look at L star. It's a very well-known algorithm. I think most machine learners have at least heard of L star. I don't know how many could re-describe it for you. Its origins come from natural language processing, where in the sort of 60s and 70s, people were interested wanted to know if, for example, the grammar of a natural language could be at least approximately modeled by a regular grammar in the Chomsky hierarchy. And rather than sort of sitting down and trying to conceptually identify the grammatical categories, it was just as easy to just train up an automata or to train up a grammatical model on what they call a corpus, okay, which is just a large body of texts. So you try to reverse engineer grammatical models from text. Again, a reverse engineering problem, right? And of course, you use Kleeni's result to say that, well, you can learn the grammar as a grammar, but you could replace it with a DFA and then convert it back if you wish. So Angerwin's approach is to learn the regular language for NLP work, but as a DFA. So this is sometimes called, particularly in the earlier literature, it's called regular inference, okay? It was the regular language. It is historically the first active automata learner. I mentioned yesterday that there's this important distinction between passive and active learning. So in passive learning, somebody gives you a set of observations, okay? And you try to fit an automata model that sort of best corresponds. And there would typically be many automata model that are consistent with the data set, so that you take on board a second criteria like state minimization. And when you take on state minimization, you basically fall into an NP-hard problem. So the subject was thought to be intractable, in fact, for quite a while, historically. An algorithm had this very sharp idea that if you allow the learner to pose its own queries, you can get into polynomial time, okay? Polynomial time modulo this equivalence checker, so one has to be a little bit careful what one says, but yes, polynomial time in reasonably strong sense. So this introduced the concept of active learning, and it's the active part that's the hard thing to learn in L-star, okay? So we'll try to focus on that today. So this brings you down into polynomial time. So the basic idea, L-star is for DFA, okay? And I said yesterday, well, not many systems in the world can be represented as a DFA. We'll fix that quite easily, okay? So DFA means two outputs. Of course, we want multiple outputs in general. We would even like unbounded number of outputs. That's all possible with L-star with the right modifications, and they're quite easy modifications. So if you're learning a DFA, so you're trying to learn a regular language, okay? Think of it in those terms. So how do you learn a regular language? Well, a language is a set of strings, right? So a query is a string. So you fire in a string and you want to know, does it pass or fail? Is it accepted or rejected? So it's string inputs and then it's single valued outputs. But of course, notice that every prefix of the string you feed in also could be accepted or rejected. So that in fact, from a sequence, from an input string of length n, you would also get n outputs, okay? N accept rejects in sequence as the algorithm works through the prefixes till it reaches the end of the string, so to speak, okay? So this is the input-output behavior. And then it synthesizes a DFA. Now, it does an important job at this point. If you just give me a data set, let's say, of strings and accept, reject statements, I can try to fit an automata to that data set. But if you just give me a random collection, it's almost certain that there will be gaps in the data set, and therefore gaps in my knowledge. In other words, there will be transitions in the model that I cannot answer what they are, because the information is missing in the data set. So what you realize is that for an arbitrary data set, you cannot give a fully defined automata model in general, okay? There have to be certain kind of closure principles on the data set. We'll call them that for now. And when these closure principles are satisfied, then you have a fully defined model, okay? So the really clever thing in L-star is to find out sufficient and necessary closure principles such that you definitely can build an automata at that point, okay? The automata construction is nothing other than a quotient construction in the sense of universal algebra, if I'm allowed to bring that in. There's not many pedagogical explanations bring that in. So the subject is highly algebraic. There's been for a long time a subject called algebraic automata theory, and this can be fitted into that background, and it makes a nicer mathematical story. So it synthesizes the DFA. It does a quotient automata construction at that point when the closure principles are satisfied. And if you just let it keep running, it will converge. Okay, which is that's rather unusual in the world of machine learning. So in my slides, I have a pretty complete description of the algorithm, but we're not going to work with that today. I'm going to work through a case study, because I think it's rather easier and quicker to look at a case study and to see how the algorithm would work on a case study. So I'm going to work with one of the simpler DFAs in the world. I don't even know what the regular language is here. I didn't bother to work it out. It has 3 states, okay? So these 2 are accepting states. That's a rejecting state over there. It's the usual formalism, okay? So we'll call this, the terminology is to call this something like the system under learning, okay? So we know it's there, but actually we cannot see this. We can query it, but we cannot see it, okay? But I'm opening up the box to cheat for you. And we know, for example, there's a regular language accepted by this thing. And what's interesting here is that we have two states. This is a minimal state automata, okay? And there, first of all, you can see that by inspection. And secondly, L star is actually will tell you that as a side effect. This is a minimal state automata, but notice there are two states with the same output. So why can I not conflate these two states, do you think? Why can I not reduce this to a two-state automata, in other words?
Because the transitions are different from Q2 and Q0.
Yeah, but we may not be able to see that from a black box perspective. If I put the lid over, you don't know that. Anything else one can say? There's something observable about this. Even if I pull the lid down, there's something observable. I'm sure you're smiling, so I think you must know the answer.
Yeah, but I think the history, so how you get there.
It's not so much how you get there, it's what you can go on to do.
Oh, okay, the future.
These things have different capabilities in the future. Okay? Even observable capabilities, and that's the key to black box learning. So I'll bring that back many times in this talk. Right, how are we going to learn this? So L star introduced the idea of organizing observations into a table. And I'll go forward to the table because the case study is so much easier to understand than the mathematical definitions here. So you either drown in math or you look at some simple graphics. So I think most people prefer simple graphics. So when we make an observation, so we start in the initial state and we fire in some, say the input alphabet is also 0, 1 here. So we fire in a sequence of zeros and ones, okay? And we land on an accepting or rejecting state. That I call 1 for accept and 0 for reject, okay? So the simplest possible I/O alphabets. So we can take that sequence, that's the input string, and we can cut it with a pair of scissors into an initial part, the prefix, and a final part, the suffix. And we can organize that data then into a two-dimensional table. So along this dimension, we list out all the prefixes that we've fed in so far, okay? Actually, we take all the strings we've fed in so far, we cut off their prefixes, we put them down the vertical axis, and we take all the suffixes that we've fed in so far, and we put them across the horizontal axis. So at this point, we have no string longer than length 2. And in fact, there's one string, 0, 1, for which we don't yet know the answer, okay? So here's a situation where we've read in 1, 2, 3. We've fed in, let's see. We're aware of 1, 2, 3, 4, 5 strings, okay? But have been cut up in various ways. So for example, we notice, so epsilon is the empty string. So we notice the empty prefix concatenated with the empty suffix. Well, that makes the empty string. And the empty string is indeed an accepted value, okay? And we can take a single 0, which is epsilon concatenated with a 0. Where does that go? Epsilon concatenated with 0 is 0, which brings us back to accept. So that has to be an accept, okay? So we can fill in this table. Now, these strings, these suffixes are not just any old suffixes. In general, we're going to try to get in across this top row these distinguishing suffixes. So we come back to this question, how do we split states? And indeed, splitting or distinguishing states is the key activity here. And the core idea, so how we can build up this table, okay? That's just an organization of data, but it's not an automata model yet. So how are we going to get an automata model out of this data set? The idea then is that distinct rows, if we look down this table at any moment in time, some rows will have identical entries in all columns and some will not. The rows which have identical entries on all points, they will all be different representatives of the same state. you could say they're observationally indistinguishable at this time, okay? And what is observationally indistinguishable? It's the prefix that labels the row, okay? So if I filled in, let's run 0, 1. Let's see if epsilon and 0 are observationally distinguishable. So there's a missing entry here, 0, 1. Okay, let's run it through. 0, 1, that's going to give me a 0. So I put a 0 there. And in fact, these two rows, if I finish the table, would be observationally indistinguishable at this time. Now, I've not done many more experiments, so it could be that later on I can separate them, right? But right now, I can't tell the difference. So this is how you get multiple models or a sequence of models coming out, because at various stages down the line, you freeze the table and you say, right, now let's build an automata out of the table, okay? And there are two steps in building the automata. There are identifying the states and identifying the transitions. Identifying the states, now you'll notice I've used different colors here. That is deliberate. There will be a set of prefixes that we call red prefixes, okay? And these are, we start off with epsilon is the initial red prefix, and afterwards I build up more and more red prefixes. There are also blue prefixes, and I will tell you that a blue prefix is always a one symbol extension of a red prefix, okay? And why do we need that one symbol extension? Because if epsilon is going to be a state when I build my model, I need to know for that state where will I go inside the model when I feed in an extra symbol, okay? So if I'm in the state epsilon and you give me a 0, I have to jump to another state. So which state will I jump to? Well, I can take the string epsilon, I can concatenate it with that one symbol, I can look down the table, and what I know, since there are blue prefixes, is that there is a one symbol extension. So this is a necessary part of the construction. There will always be blue prefixes where I can find a one symbol extension. So I can notice I cannot find if I concatenate epsilon with 1, that's missing at the moment, isn't it? So I don't know where to jump on 1, but I do know where to jump on 2. I'll jump to this row here, and since we know that's a 0, I know where to go because there's actually a red prefix, in other words, a state known in the model where I can go. So it's nothing other than this transition here, okay?
May I ask something?
Yes.
What is the difference between epsilon 1, which is in the table, and 1 epsilon?
1 epsilon would be, the 1 would be down here, and the epsilon would be down there, and the value would be there.
So why isn't it then there? Because the epsilon 1 is...
I just haven't put it there yet, okay? At any, if you stop the algorithm at any time, you'll find you've done some things and not done others, okay? So you're not necessarily closed. If
1 comes, you always put in the 1 as a postfix, a suffix. Or because
you can represent it either way around.
so why did you do it this way? Because the epsilon 1 you already had, and you entered a 0 for that.
Oh, did I not fill out the table here? No, but this is the string 0, 1. Here.
No, the epsilon in the row, the last entry.
Right.
Epsilon 1
Yeah.
is a 0. So
Oh, I can carry, but I mean, there's a certain symmetry of the table. That's true, yes. This is not even a symmetric table, right? It's wider than it is deep. I'm just trying to keep the everything simple, okay?
I see.
We'll see how this, so this table is going to grow over time, okay? And it's kind of the essence of active learning, how you grow it, okay? So the growth itself is the active learning. So this table will become bigger, it will become deeper. Sometimes it will become deeper, and sometimes it will become wider, okay? It never does both simultaneously on the same step, okay? And it will also need to be filled in. As you expand it downwards or sideways, you'll automatically open up gaps in the table, and these gaps must be filled in. Okay? So you can never do the automata synthesis without a completely filled in table, but that in itself is not a sufficient condition to build an automata model, okay? We must have closure as well. So there are two principles going on, I would say, in DFA learning. How do you learn about a DFA? There are two things. First of all, if you've never ever visited a state, and particularly if the automata is a minimal state automata, if you've never ever visited a state, it's not possible to know anything about that state, okay? That's just natural human intuition, okay? If you've never been to Halmstad, you don't know what the railway station looks like, okay? So we need access to strings. In other words, we need prefixes that reach every distinct state, distinct in the sense of minimality, right? Of course, if it's non-minimal, there are different representatives of the same state, and it doesn't matter which you reach, in fact. So we don't know if the thing inside the black box is minimal or not. But as I said previously, and I even promised I'd come back to it, it's not enough to access states, you must also distinguish states. So if we go back to our running example, we access this state pretty quickly because epsilon takes you straight there, and it's an accepting state. And we can access this string also quite quickly, and it's also accepting, but they're not the same state. And what distinguishes them? A certain suffix that we have to find. And in fact, I would say the job of finding the distinguishing suffixes is computationally somewhat harder. I'll show you the evidence for that later on. So we have to find states and we have to distinguish states. And the inference principle is actually rather crude, I would say, by the standards of machine learning. So there are much more. All machine learning is really about inductive inference, in my personal opinion. That is to say, from a finite data set, extrapolating, interpolating, whatever you want to call it, values that you've not seen before. Okay? Whether these are the values of a function or a relation or an automata or whatever. You want to sort of implicitly infer them. And loop identification, as we mentioned yesterday, is part of that, okay? So you never see a loop as such, okay? But you implicitly infer that it could be there, right? So here's our principle here. If we look at this two-dimensional table, okay? So this is the entry in row prefix or row P and suffix or column S, okay? So given two rows or prefixes, P and P prime, they cannot possibly be accessing the same state if there's some column entry across those two rows that differs, okay? It's not possible because what that says is they have two subsequent behaviors that are different. And if the underlying model is deterministic, there's no way that can happen. Of course, if it's non-deterministic, that principle is a bit unclear, right? A bit unclear. Nevertheless, one can do automata learning for NDFA. But under assumptions of determinacy, this must hold, okay? So we must always get the same behavior every time we arrive at the same state. And then we simply don't. Now, so that is the basic thing. So that comes back to what I said before about state identification, okay? The distinct rows uniquely identify the distinct states in the final learned model. But this is not enough, okay? What is not enough is to guarantee that when you do the model construction, you won't run out of information. There won't be gaps in your knowledge. So how do we ensure there are no gaps in our knowledge? There are two principles here. Let me see. They're reasonably quick to show, so I'll show them. One, it says that if you take it, so our states are going to come from our red prefixes, okay? And I said, well, there are also blue prefixes, and these are one symbol extensions of red prefixes, okay? So closure, this is really an algebraic closure condition, but the books or the papers never tell you that. For every red prefix, and for every one symbol extension, there is a blue prefix which has the same row. So if this blue prefix is the same row as that red prefix, then I can say that that one symbol step takes you to this red state. And it is a well-defined red state, okay? So there's something in the automata that it corresponds to. So this is like an algebraic closure condition, right? The state set, the putative state set, which is all the red prefixes, is closed under one step. In other words, the delta operation in the model, okay? So the delta operation will be closed. And with the delta is very much what we're looking for. There's another thing here, and it's a kind of a resolution of ambiguity, or you could say the fact that you can build a DFA at all, which is non-obvious. I'll come back to that remark in a minute. Oh my word, I'm running way over time. But Valida's gone, right? So I can do that. So consistency says that if you take two rows, and if you take the same one-step extension, you get to the same two rows, okay, in terms of representatives. So it's a determinate automata under the delta function. Said differently, this equivalence relation on rows is congruent with the delta operation. It is a congruence in the sense of algebra, okay? So we have a set of states which is algebraically closed, and we have a congruence we can apply. So we can make a quotient automata. And that's actually what happens, okay? Let me skip forward. Well, yeah, I'm running vastly over time.
Actually, you still have 15 minutes started.
Oh, yeah, yeah. Oh, great. Excellent. Sorry, I misinterpret my own clock. I'm too busy thinking about other stuff. Right. Well, we'll come back and show an example. I'll show you some of the properties of L star, and then maybe we'll look at it executing. So here's the basic result. First of all, there's a hell of a big assumption here. There's a black box hiding a computational mechanism. We know nothing about it. We don't even know if it's a DFA. It could be a push-down automata. And what do we know about push-down automata? Not all reducible to DFA, right? So if it's a push-down automata, you can think about this on the way home. What happens if I run L star on a push-down automata? And I won't tell you the answer here. So, but if the thing inside the box is representable by a DFA at all, which is an unknown, and if it's representable by DFA, then of course it has a minimal representation in terms of state space compaction. Then L star eventually terminates. In fact, L star would terminate even if it was non-minimal. But if A is the minimal representation, then L star terminates. It gives you a DFA structurally, that is to say graph theoretically isomorphic to A. So in other words, L star always computes the minimum state representation naturally. In fact, of all the automata algorithms I've ever seen, I would say it's very rare that you get a non-minimal state representation. But you can, and there can even be sometimes reasons why you would want that. So you can sometimes tolerate a certain amount of state space expansion to achieve other aims, okay? But here we always get the minimal state automata. I'm going to simulate the algorithm, and we'll see that we get back what we put in here. So there, that's the basic observation. It terminates, and it always terminates. Complexity. This was the reason that L star got the attention. It was originally really a complexity theoretic result, because people were skeptical of automata learning as a... so Gold wrote a paper in '78 that said, well, you know, passive automata learning is NP hard, and at that point a lot of people gave up. So there's almost a 10-year gap here before L star appears. And in her paper, Anglin proved that, in fact, active learning can be done in polynomial time. So this suddenly sort of reopened the field. And then in NLP, there was a lot of attention then refocused on this. So many algorithms have appeared since L star, and a lot of papers, a lot of survey papers, and so on. There's something I'm missing out here, which is equivalence checking. So I'll come back to that. So let's just ignore this remark for the moment. And I've got the actual complexity results somewhere. So the theoretical complexity can be seen as follows. So we measure complexity in terms of the number of queries needed to learn an automata. So if sigma is the input alphabet size and q is the state size, and what is, let's see, so the initial result is that if you can find a bound m on the natural length of any counterexample, what's the counterexample there? Well, in active learning, you sort of refresh or extend the automata model. So you start off with small, slightly bigger, slightly bigger, slightly bigger. And you reach these sort of local fixed points when you're closed and congruent, okay? But then what? How do you go beyond there? You have to do something called an equivalence query. If you've not terminated yet, if you've not finished learning yet, if you run an equivalence checker, and there are many kinds of those, some are glass box, some are black box, but if you've not finished learning yet, an equivalence checker is able to produce a string which behaves differently on the system under learning than it does on the currently inferred model, okay? So they're not, you could say, observationally equivalent. There's at least one counterexample. And we use this counterexample to kickstart the next learning phase, okay? So we can look at the length of that counterexample, and this can, for example, be bounded because you need to look for nothing longer than the size of Q itself. So taking Q as a bound on M, then we see that the complexity of learning is upper bounded by that, okay? And then I've got some empirical results on the complexity of learning, which is quite interesting. See if we get time to look at those. Now, I wanted to actually run L star because I think it's the easiest way. So you have to build an initial model, okay? And you have to start from an initial table. The initial red prefix, there's just one. It's epsilon, okay? This is the canonical red prefix. So you always start here. And we naturally need to know all its one symbol extensions, okay? So we can run these queries. And we don't need any suffixes other than epsilon to get this table here, okay? Now, in terms of consistency, there's no ambiguity, but this is not closed because if I start from epsilon and I feed in a symbol 1, I get to a row with a 0, and there's no red row 0, okay? So we're not algebraically closed at that point. The delta operation, if I tried to define it on this table, it would not close up. I couldn't define delta epsilon 1, okay? So green is the problem here. So here is the first step in active learning, right? Active learning says, well, there's something that I don't know. I can see this. So I know of something I don't know. In a strong sense, active learning uses the fact that you know what you don't know, okay? And you use that to progress forward. So I'm going to promote 1 to a red prefix. Now it's become a red prefix, it needs all its one-step extensions, doesn't it? So if 1 becomes red, I need to know 1, 0 and 1, 1. So I find them out, okay, with extra queries. This table is now both closed and it's also consistent. It's consistent because actually, for a trivial reason, there are no two isomorphic rows right now. There's a 1 and a 0. And consistency says if you start from 2 rows which are point-wise equivalent and take the same step, you must end up in 2 rows which are point-wise equivalent, okay? But that's not an issue here because we don't have the equivalent rows to start with. So it's trivially consistent and it's by construction closed. Great, now we can make a model. So the states, there are 2 of them because there are 2 distinct rows. And there's the row 1 becomes this thing, and the row 0 becomes that thing. And the delta is defined for all of these states, okay? Because I know a 1 step for epsilon, and I know a 1 step for 1. So I have all the information to derive this thing. And it's not so obvious that it's a quotient automata construction, but if you read our survey, we go into in a little bit of depth, you know, what is the quotient automata construction here. So it is that. You'll have to accept it for now. So here's our initial guess, okay? It's quite clearly...
What's the initial state?
So, sorry, yes, the initial state is always, always, always epsilon. There's a question you haven't asked, which is what if you get 2 rows which are equivalent? Then it looks like you have 2 prefixes or 2 potential names for the same state. What do you do then? The convention is to, using the lexicographical ordering, take the first one, okay? So that's how you resolve that ambiguity. Now this is 2 states. We know that it's minimal, okay? And our other automata is 3 states, and it's also minimal. So there's no way these two automata can be the same right now. So if we ran an equivalence checker, there would be many counterexamples, some longer than others. And here is certainly one counterexample. So if we run this string on those two automata, the 3 that we're trying to learn and the 2 state that we have learned, you'd see a divergence here, okay? So what do we do then? So you can break the L star algorithm down into 2 routines. One routine that I would call get initial hypothesis, and I do that in the slide, so you can read the algorithmic description later. So there's a get initial hypothesis, and then there's a get next hypothesis. And you call get next hypothesis again and again and again. And every time you call it, it will return a new model, okay? You call it with one parameter, and that parameter is a divergent string, okay? So it needs an input parameter to start. And what does it do with this divergent string? It adds it as a red prefix, okay? And as soon as I've added it as a red prefix, I need all its 1 symbol extensions. So with a 0 and with a 1, that has to be filled in. And then you get a certain table. So you build out the table, you fill in the gaps, and then you ask the questions again, am I closed or am I consistent? Here we happen to be closed, but we're not consistent, and there are 2 inconsistencies here. So the row for epsilon and the row for 1, 1 both give me the value 1. But if I do a 1 extension of these things, I'll see that 0 is not equal to 1. And if I do a 0 extension, I'll again see that 0 is not equal to 1. So there are 2 failures of consistency right now, okay? So I have to fix those both. And how do we've seen how you fix closure, okay? So you promote a blue to a red, and then you build it out. How do we fix consistency? Yeah, nearly finished. You fix consistency by taking the violating strings, okay? There were 2 of them. So these are actually distinguishing suffixes. So I build out the columns with both distinguishing suffixes, and then I fill in the entries, okay? So I resolve these 2 inconsistencies. So that is going here and that's going there. Build out the table, and this is now both closed and consistent. Which means I can build a new automata. And lo and behold, do I have it anywhere? Well, I didn't draw it, but lo and behold, you get back the original automata. So we've terminated, okay? So these problems in the table are the source of the active queries, okay? So the basic gaps, which already arise when you get failure of an equivalence check. So the basic gaps, plus resolving closure, plus resolving consistency. All of these things are deterministic problems to be resolved, okay? So there's an algorithm called make closed. There's an algorithm called make consistent. So this is how the active querying it comes about. Where do I want to finish? I have 2 minutes left. Let's just look at an interesting behavior here. There are many questions about, how does this work in practice, and does it work, on large-scale automata? And if it goes wrong, what goes wrong? We did, in general, very quickly you realize that some automata are much harder to learn than others. And one of the things that we wanted to understand is what makes an automata hard to learn. So you can take 2 automata of exactly the same state space size, right? They're minimal, they have the same number of states. But one of them will take a heck of a lot longer time to converge than the other. So what influences that? One would very much like to know. We did a master student of mine did a very nice experiment. So he built minimal automata of a certain size, and then he randomly labeled them with 0s and 1s, and measured the number of queries needed to learn. So you notice this is a 50% random distribution of 0s and 1s, okay? And you can push it out in either direction to have probably almost no accepting states, or I think it's the right way around, almost no rejecting states. And as you push it out, it gets vastly more difficult to learn, okay? Substantially more. I think when you fit the data, these are quadratic curves. So it gets substantially more difficult to learn. I'm running out of time, so I can't go into that. I can say more. Okay, we don't really have the time today. What did I want to finish on? I wanted to finish on maybe this thing here. How do we, of course, DFA are not very exciting beasts in the world unless you're a natural language person. How do we build this out to something that can handle the real world? Well, you notice these are rows of zeros and ones, okay? Everything I've said generalizes to any finite alphabet here, because on a finite alphabet I can always ask for 1 or 2 rows identical, okay? That's what we're talking about. I can even build these out to, I could even put reals in here, okay? Assuming I can distinguish exactly 2 reals, but I can certainly deal with floating points or rationals or whatever your favorite computational model is. Or I can have integers in here. So you can actually, you don't need a bounded output alphabet. You do need a bounded input alphabet because you can only ever sample from a finite space, okay? Because time is finite. But you do not need to bound the output alphabet size. Next thing you notice, well, how to deal with non-determinism. A cheap and cheerful model of non-determinism is to make these things set-valued, okay? So you add the outputs as a set. That is a little bit strange because it gives you an internally deterministic automata which is set-valued on the output. So that's not actually how people do NDFA in practice. There are other things you can do. You can modify the congruence construction is one way to go at it. But you see, if you follow this principle of congruence all the way through and you keep following it, you can add probabilities because you can build up the observation table. You can sort of repeat the same query many times and see, well, how many times did you get A? How many times did you get B? So probabilistic automata are an extension of non-deterministic automata where we quantitatively measure the behavior. And then you put these quantitative measures into the congruence construction, okay? So you say when are 2 rows in a sense sort of probabilistically close, okay? We use something like a Hufting bound there to sort of extend the congruence notion. You can also extend the whole concept with registers that can do more interesting things that can just jump to the next state. They can do a computation on the way. So there are things called register automata, which are a little bit like learning state charts, if I can call them that, of a very restricted form. So by pursuing this congruence construction to the bitter end, okay, you can carry this story through to really a wide variety of automata. Timed automata, I think, are another example that works here. And I think we actually saw the congruence construction yesterday secretly in your talk. So it works. So the quotient construction is all over mathematics because it's so universal and incredibly powerful. And it works in this part of the world. So I should stop there, I think, because people want a morning coffee. I do. Yeah. Tomorrow I'll show you some nice films and it won't be so difficult to understand, and we'll look at this sort of applied industrially and platooning and so on, okay?
Thank you. Thank you very much, Karl. Any questions? I have a quick question. So when you mentioned the NDA extension, you said that you can have set-valued outputs.
That's one approach.
And then in that case, do these states represent the equivalence classes of the...
It must be something like that. I've not worked out what it would be. It must be something like that.
Okay, so at least it's a good starting intuition.
It's a very easy algorithm to implement, yes. But what you can't then analyze is the sort of the non-deterministic behavior internally, okay? Which is typically what people actually want to know about. So it's sort of a poor man's solution, if I can call it that, without being sexist.
In a way to...
A poor person's solution.
In a way it avoids a lot of the complexities that could come with...
It is a rather compact way to learn, yes.
Yeah. So it's very interesting. One can even take an undeterministic automata that they know about and apply the algorithm and see what they get on the other side. The
L star is quite easy to implement and experiment with. If you're interested in finding more about these algorithms, there's a package called LearnLib out on the web, which is an open source, where you can do some experiments. Yeah. I'm not sure all the algorithms. I'm not sure they have. I'm not sure they have probabilistic learning in there, or timed learning, but they have the basic automata.
So what was the answer to the if the black box is not a DFA, so if it's pushed down?
Oh, that's too early. Come on.
Okay. All right.
Is this a kind of reverse of the minimization algorithm?
You kind of get minimization here for free, because if it were to be non-minimal, right, you would have to distinguish two states without having a distinguishing suffix to distinguish
That's
them.
what I mean.
So what the heck else would you use at that point, right?
No,
So
I
it
mean,
almost comes
this
for
table
free.
remind me of the minimization, because the minimization you do nature the same way. You search for distinguishing strings.
Yeah, that trick is there, yeah.
And
yeah.
now you do the same,
Mm,
but you do not know the size of the table. So you get.
yes, yeah.
This is very interesting, and that's why I
It's
asked.
connected. I wouldn't like to say it's the same. There are some connections. It's a bit different when you don't know. In minimization, you've got a starting automata and an end automata. But here we have no start automata, okay?
Yeah,
And
that's
the
why
whole
you
point.
don't know the size of your matrix, but
Yes.
you guess first. You guess and check whether it works, and if not, then you enlarge in your matrix. But
There's-
it is very interesting.
There's another subtle point here, which is that to guarantee the proof of convergence relies on having an equivalence checker that always gives you an answer if there is one. There are glass box checkers, the best known as the so-called Vasilevsky-Chow algorithm. That has the unfortunate property that the computation time is exponential in the difference in state space size between the automata you currently have and the target automata. So it can be very slow, okay? But it is sort of, sorry, did I say? No, it's a black box checker, but it's an exact checker, okay? We, in our work, we use stochastic equivalence checking, because then we don't run into that problem, and we feel that stochastic equivalence checking, in other words, just randomly sampling, okay? So a Monte Carlo approach to equivalence checking. We use that because it is related to risk factors, reliability factors, and it also connects to pack learning. So I had an offhand. I hope people are familiar with the pack paradigm, probably approximately correct. I had it somewhere. Where's it gone? So if you don't believe, oh, it's gone somewhere. Never mind. If you don't believe in exact checking for various reasons, or glass box checking, so you can't suddenly introduce most equivalence checking algorithms are glass box. You can't suddenly introduce a glass box equivalence checker into a black box learner, right? It's fundamentally cheating. So you're restricted to black box checkers, and there are not many. So there's Vasilevsky-Chow, which is deterministic, and then there's stochastic, which is non-deterministic, right? And when you take that route, you get into a probabilistic result. So you will converge with a certain probability and a certain accuracy. And that works too, in polynomial time.
Do you use assembly solving for those checking? For the equivalence checking, and also for finding corrections?
There are SAT approaches to the whole subject, yeah. I've never studied them very closely, but
I
they do
think that's
exist.
very promising, because you can even do several steps.
I'm not sure what the scalability would be like. Scalability is the absolute necessity here.
Yeah, but this is just combinatorial optimization. This is the main strength of SAT solving.
Tried. Okay.
Very interesting. Any other questions? Good. Thank you very much, Karl.